Good morning, everyone. As I have said last time, solving differential equations depend on what kind of differential equation we are solving. So the solution varies depending on the differential equation we are solving. One type of differential equation that we are interested in solving are homogeneous differential equations, or differential equations composed of homogeneous functions. There is a test in order to determine if the function is homogeneous, and we call that the test for homogeneity. Test for homogeneity. Right? And the test for homogeneity states that for a function f, which is a function of x and y, if you insert a coefficient, a particular coefficient to every variable x and y within the function, that is, let's say lambda x and lambda y, and if you can separate the lambda, if you can factor out the lambda, that variable, and to a degree of k, and there is no variable left within the function, then we can conclude that the function is homogeneous. The function is homogeneous. And that is homogeneous of the degree k. So once again, if you have a function composed of x and y, a function of x and y, and you insert a constant, a particular constant, let's say lambda, to both x and y, and if you can factor out lambda from the function, wherein the function would no longer contain that constant which you inserted, constant coefficient, then the function is homogeneous of the degree k. So we will solve some examples regarding this. For our first example, let's say we have 4x squared minus 3xy plus y squared. To test this for homogeneity, we insert a constant coefficient, let's say a lambda, with every variable. So since this is x squared, so we insert lambda and as a coefficient of x squared minus 3 lambda x lambda y, okay, plus lambda y, and since y is squared, so we square both lambda and y. And so by rules of exponent, we have lambda squared x squared minus 3 lambda squared. Lambda times lambda is lambda squared xy plus lambda squared, again by the laws of exponent, lambda squared y squared. So this time we have a common monomial factor, which is lambda squared. All the three terms contains lambda squared, and so we can factor out lambda squared from the polynomial. So we have now 4x squared minus 3xy plus y squared. And since we have factored out lambda and there is no lambda inside the function, we can say that the function is homogeneous. Homogeneous, and what is the degree? The degree is second degree. Second degree. Right? So that is our first example, in order to determine whether a function is homogeneous or not. For our second example, we have x cubed minus xy plus y cubed. Again, we insert a coefficient to all the variables within the function, in this case x and y. So we have lambda x, and since it is attached to since it becomes the coefficient of x, it becomes cube as well. So minus lambda x times lambda y plus, again, lambda y cube. As you can see, it is already obvious that we cannot, all the lambdas that do not have the same power, so we cannot factor them out. But just to continue the process, we have lambda cube x cube minus lambda squared x y plus lambda cube y cube. And since we cannot factor out the lambda without having a lambda inside, because if we can factor out actually lambda squared, but then we will have lambda inside the function minus xy plus lambda y cube. We have factored out lambda squared, but we cannot factor out all the lambda inside. So this function is not homogeneous. And since it's not homogeneous, we do not have to place a degree. Our third example is 2y plus square root of x squared plus y squared. So we have here 2 lambda y plus square root of lambda x squared plus lambda y squared. Okay, so what we do is we simplify. So we have 2 lambda y plus, we have lambda squared x squared plus lambda squared y squared. Inside the radical, we can factor out the lambda. Actually, we can factor out lambda squared, and we have x squared plus y squared. If you remember, one of the properties of radicals is that we can separate the radicals that are we can factor out. We can factor two radicals that are multiplied inside. So we have lambda squared, square root of x squared plus y squared. Okay, so we can separate them into two factors. We can cancel this and this. So we have 2 lambda y plus lambda square root of x squared plus y squared. And since we have lambda per term, we can factor out the this lambda. We have 2y plus square root of x squared plus y squared. So we have completely factored out the lambda so that we no longer contain any lambda inside the function. And this means that the function is homogeneous. And since it is raised to an exponent equal to 1, then we can say that it is homogeneous of the first degree. Okay? Our next example is square root of x minus y. Again, we insert lambda for every term. And since every term has a lambda, which is a common monomial factor, we can factor it out. So we have x minus y. And then by the Prince laws in solving radicals or simplifying radicals, we can have square root of lambda times square root of x minus y. And here we can convert the radical into an exponent, which is 1/2. Then we have square root of x minus y. We now have the original function, and since the original function doesn't have any lambda in it, so we can say that this function is homogeneous. And what is the degree? The degree is equal to 1/2. The seventh example is e to the power of x over y. Again, we test this for homogeneity. We simply insert constant lambda for every variable. Okay? And what do we do with lambda? We can cancel lambda out. So we have now to the power of x over y. You can see that we have already obtained our original function, and it is free from lambda. It is free from lambda. But then we can also say that we can this function is unchanged if we multiply it with lambda raised to the power of 0 times to the power of x over y, because lambda to the power of 0 is 1, is equivalent to 1, because any number, once again, raised to 0 is equal to 1. And so since we have already obtained our original function free from lambda, we can conclude that the function is homogeneous. And it is homogeneous with having a degree equal to 0 or 0 degree. Next, we have x squared plus y squared times e to the power of 2x over y plus 4xy. Again, we insert lambda for every variable involved. So lambda x squared plus lambda y squared times e to the power of 2 lambda x over lambda y plus 4 lambda x times lambda y. So we have now lambda squared x squared plus lambda squared y squared, and here we can cancel out lambda and retaining 2 e to the power of 2x over y plus 4 lambda squared xy. And we can factor out lambda from here. We have lambda squared x squared plus y squared e to the power of 2x over y plus 4 lambda squared xy. Here we have two general terms, this term and this term, and they both contain lambda squared. So we can factor out lambda squared, and we are left with x squared plus y squared e to the power of 2x over y, I'll place a square bracket here, plus 4xy. Now, we have already obtained the original function. This is the original function, and it doesn't have any lambda at all. It doesn't contain any lambda at all. So therefore, we can conclude that the function is homogeneous. And to what degree? To the second degree. Our next example is y squared tangent x over y. So once again, we insert lambda here for y, tangent lambda x over lambda y. So we have lambda squared y squared, and lambda cancels out here. So we have now tangent x over y. And since we can, by associative principle, we can have lambda squared y squared tangent x over y, that is associative property of multiplication, where we can group this factor together. And since this is already the original function, we can conclude now that the function is homogeneous and to the second degree. The function is homogeneous to the second degree. For our last example, we have x ln x minus y ln y. So we have here, we insert once again our constant coefficient lambda x, ln lambda x minus lambda y ln lambda y. Okay, so what we will do is we can factor out this lambda here. So we have lambda times x ln lambda x minus y ln lambda y. But as you can see, there is no way we can factor out lambda inside the logarithm. So that means this, we can conclude that this function is not homogeneous. Even if we process it further, we manipulate it. Let's say we have lambda x ln lambda plus ln x, because we can, this is a property of logarithm, minus y and then ln lambda plus ln y. Okay. So still there is no way of having this lambda factored out. So we can conclude that for this function is not homogeneous. Okay?